The examples for this lesson come from lesson 4.1, Basic Ideas of Probability. Example 1. A family has 3 children. Denoting A, boy, by B, and a girl by G, we can denote the genders of these children from oldest to youngest. For example, G, B, G means the oldest child is a girl, the middle child is a boy, and the youngest child is a girl. There are 8 possible outcomes: G, 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 B, G, B, G, G, B, 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 G, G, B, G, B, 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 G, and B, B, B. Assume these outcomes are equally likely. A. What is the probability that the youngest child is a boy? Alright, to find this probability, we need to find the number of outcomes in our sample space, which is located right here. These are all my outcomes. And we are looking for the ones that have a boy in the 3rd position. Alright, that happens with this one, this one, this one, and this one. All of these outcomes have a boy in the 3rd position there. So the probability that the youngest is a boy is the number of my outcomes that have a boy in the 3rd position, there are 4 of them, divided by the number of items in my sample space. And there are 1, 2, 3, 4, 5, 6, 7, 8 of them. So the probability is 4 over 8, or 0.5. B. What is the probability that the oldest child and the youngest child are of the same gender? Alright, so let's go back and erase these. And this time we are looking for the oldest child in the 1st position and the youngest child in the 3rd position having the same gender. That happens here because we have a girl and a girl. It happens here because we have a girl and a girl. It happens here because we have a boy and a boy. And it happens here because we have a boy and a boy. Alright, and so the probability that the oldest and the youngest have the same gender is the number of our outcomes that have the oldest and the youngest the same, there are 4 of them, divided by the items in the sample space, and we already said there are 8 of them, and so this probability is 0.5. Example 2. A penny and a nickel are tossed. Each is a fair coin, which means that heads and tails are equally likely. A. Construct a sample space containing equally likely outcomes. Each outcome should specify the results for both coins. Alright, so for A, our outcomes are going to be, we could flip ahead the first time on the penny, and then we could flip ahead on the nickel. We could flip ahead on the penny and a tail on the nickel. We could flip a tail on a penny and a head on the nickel. And we could flip a tail on a penny and a tail on the nickel. That is our sample space. Now B, find the probability that one coin comes up heads and the other comes up tails. So we are looking for the outcomes where they're different. We don't want this one because they're both heads, they're the same. But here, the penny and the nickel have different outcomes, And here, the penny and the nickel have different outcomes, but down here, they are the same. Right? So the probability of the head and the tail let's try that again. The probability of one head and one tail is going to be the number of our outcomes that have one head and one tail, there are 2 of them, divided by the total number of members in our sample space, and there are 4. And so this is going to be, again, 0.5. Example 3. There are 100,000 voters in a city. A pollster takes a simple random sample of 1,000 of them and finds that 513 support a bond issue to support the public library and 487 oppose it. Estimate the probability that a random chosen voter in the city supports the bond issue. Alright, so we are looking for the probability of voter support. And this will be the number of people who support the issue divided by the total number of people in our sample. And up here, it tells me that 513 support the issue, so that's going to be our numerator in our fraction. And then our sample space will be right here, the sample of 1,000 people. Right, and so our decimal is going to be 0.513.